So in today's lesson, we're going to be following up from our Desmos activity where we investigated transformations of quadratic functions by looking at how if we change that basic quadratic function y equals x squared, how that changes the shape of the graph. So let's think for a minute about what it means to transform something. So when we transform something, we change it into something new. Usually it has some semblance of what we saw before, and certainly that's the case when we look at our quadratics. So in yesterday's activity, I'm hoping that you saw some of the following things. I'm hoping that you saw that we can, and here's my graph of y equals x squared. I'm hoping that you saw that by changing aspects of the function, I could get graphs that were narrower, I could get graphs that were wider, or appeared wider, and I could also get graphs that seemed to be flipped upside down. Now all of those are transformations, and so today we're going to just break that down and kind of delve into it a little bit more deeply. So when we talk about transformations with respect to math, a transformation is basically a change that we make to a relation or function that basically results in a new relation or function. So for a quadratic function in the form y equals ax squared, and we certainly saw that in our activity, we saw that by altering the value of a, that coefficient of x squared, we were able to change the shape of the graph. So let's consider first our graph of y equals x squared. What is the value of a in this function? Well, there's an understood 1 beside our x squared, so we can say that the value of a in our standard function is 1. And we know that when we multiply anything by 1, we don't change it. So what we're going to do in this, what we did in our activity and what we're going to investigate further is, well, what happens if the value of a, if the value of a is not 1? So I'm hoping you'll remember that from yesterday's activity, if the value of a, if the coefficient of our squared term is a positive number, then the parabola is going to open upward. So if the sign of a is positive, then we're going to see an upward opening parabola. So I just want to remind you of how we are going to graph that standard parabola. Now, of course, we can always use the coordinates, the xy coordinates for that, so x and y. I get y by plugging in values for x. So if I have a 1 for x, then 1 squared will give me 1. If I have 2 for x, then 2 squared will give me 4 for y, and so on and so forth. But you may remember that I also provided you with a quick trick, which was the 1-3-5 method, which we can use if we're graphing y equals x squared. It's nice and easy. So I'm going to do that. So 1 and 1, 2 and 4, and what I didn't include here was 0, 0 as another possibility. So, but again, I can always use my 1-3-5 method, which is the over 1 up 1 over 1 up 3, and then use the axis of symmetry to help me plot the mirroring points. And there I go. Now try to make your graph a little smoother than mine. Mine, it's hard because I'm using a stylus on an iPad, but you want to endeavor to make that just a little bit more smooth than I've done. Now, of course, this is our standard parabola, but we also should note that it is upward opening, and that is because the coefficient of x squared is a positive value. Now, again, in yesterday's Desmos activity, we saw that if the value of a, the coefficient of our squared term, happened to be a negative number, then what that would do is flip our parabola upside down. In other words, our parabola would open downward. So a quick way to do a simple reflection of this would be to take our y equals x squared and simply flip it upside down. But sometimes we'll have more than one transformation to consider. So I'm going to show you a couple of different ways to do this. So I know that my graph y equals x squared is going to be transforming into y equals negative x squared. So what that means is that every xy coordinate of my original function is going to transform. I'm not changing my x values, but all of my y values are going to become negative, right? That's what it means when I say y is going to become the negative of whatever x is, and then we're squaring it, right? That's how we're getting those values. So in my original function, I've got y equals x squared, and we can come up with a bunch of coordinates for that, right? Which we know 0, 0, 1, 1, 2, and 4, and so on. And those are all going to be transformed. So of course, my x value is not changing according to this formula, and the negative value of negative 0 is still 0. One is not changing here, but then I'm going to have the negative of whatever my y value was, so negative 1, and then 2 and negative 4. So all this is going to do is simply flip my graph upside down. So another way that we could have done this was to say, well, I know my 1, 3, 5 method, right? Except I know that it's going to simply be flipped upside down. So instead of moving over 1 and up 1, I'm just going to move over 1 and down 1, and then over 1 and down 3, and so on and so forth. And that is a quick trick if you have just a simple reflection to do. And so I'm going to do that. And then I'm going to, of course, mirror my coordinates on the other side of my axis of symmetry. And then I'm having a hard time here with my stylus. And then try to draw a nice smooth curve in there. Okay, so again, these are two different strategies. I can take my existing coordinates and transform them and then plot those points, or I can use a quick trick here using my 1, 3, 5 method, because this is a simple single transformation. So again, this is what we refer to as a reflection in the x-axis specifically, because we're thinking of the x-axis as almost a mirror, so it's reflected in that x-axis. So the next type of transformation that I want to talk about is a stretch or a compression. So a stretch will typically make, if we're talking about a vertical stretch, will typically make the graph narrower, and a compression will actually make the graph wider, which seems counterintuitive, but if we're talking about a vertical compression, then we're just squashing it down in the vertical direction, and so that will make it the graph appear wider. So yesterday we saw that if the value of a was greater than 1 or less than negative 1, in other words, if it was not a fraction less than 1, okay, if it was a whole number, whether negative or positive, then we saw that that had the effect of making the parabola narrower, right? Well, what we call that is a vertical stretch, okay? We say that the graph is stretched vertically. So what I've got here already on my graph, on my grid, is y equals x squared, our standard parabola. And so if I look at the function that I want to graph, which in this case is y equals 2x squared, I can see that if I look at my standard formula for a quadratic, y equals ax squared is what I'm looking at so far, then I can see very clearly that the value of a is 2. And so what that's telling me is that this function is going to be transformed from y equals x squared, and it's going to have a vertical, I'm going to write v because it's easier, vertical stretch by a factor of 2. So what does that mean? Well, I know that I'm taking y equals x squared and I'm transforming it into y equals 2x squared. And so every x y coordinate in y equals x squared is going to be transformed into x and 2y. So basically, when I look at this function, I see that every y value is going to be multiplied by 2 compared to the original function, which is why I can say, well, y becomes twice what it was before. So I'm going to start with some of my basic coordinates, and sometimes you need to expand on them in order to get enough of the graph to be able to sketch it accurately. So oopsies, I'm going to go 0 and 0. And so my x value is not changing, but I'm going to multiply my y coordinate by 2. But when I multiply 0 by 2, then I still get 0. And so on and so forth. So 1 and 1 will transform into 1 and then 2. 2 and 4 is then going to become 2 and 8. And I think I have enough nice coordinates to graph, so I'm going to go ahead and plot that. So now in simple, nice, easy numbers, with nice, easy, simple numbers, we can actually just do this if the graph of y equals x squared is already there, simply by knowing that all of my y values are going to be doubled. So since right here I'm at y equals 1, the transformed part will just be twice the distance from my x-axis, so it'll be at 2. Over here where my y value is at 4, I can simply just double that, knowing that it's going to be twice as tall, or stretched to be twice as tall, so that's coordinate's going to move to 8. And of course that I can see in my coordinates. But if you prefer to have it nice and organized, and that's simpler for you to manage, then by all means use the coordinates that we mapped out there. So 1 and 2, and then 2 and all the way up to 8, and that looks like that's all I'm going to be able to graph on this grid. And then of course I'm going to mirror using my axis of symmetry, which is my y-axis, and there I have it. So there is my vertical stretch factor of 2, and as we would have anticipated, the graph is narrower than my original function. Now, in our Desmos activity, we also saw that if the value of a was between -1 and +1, in other words, if it was a fraction that was less than 1, then the parabola had the effect of appearing wider, right? Now, it appears wider, but all we've really done is just sort of squashed it down vertically. So imagine you have a hand up here and a hand up here, and you're just sort of squashing it down. So we say that it is compressed vertically, or it is a vertical compression. So when I look at my graph here, or my function, and I compare it to y equals ax squared, the standard function, I can see that the value of a is 1/2. And that's what's telling me that this is a vertical compression. Okay, so if I choose to, I can show the mapped coordinates. So y equals x squared is going to transform into y equals 1/2 x squared, so that every y value in my original function is simply going to get multiplied by 1/2 or divided by 2. So looking at my mapping my points, x and y is going to become, well, nothing's happening to my x because it's not a horizontal movement, it's a vertical compression. And so every y value is going to get multiplied by 1/2 or divided by 2. So I've got my standard coordinates here, 1 and 2. Oops, nope. I'm going to start with 0 and 0, and that's going to stay as 0, 0. Notice my vertex is not changing with a compression or a stretch. Then I've got 1 and 1, and that's going to become 1 and 1/2 or 0.5, whichever you prefer. I've got 2 and 4, which is going to be become 2 and 2, and 3 and 9, which is going to become 3 and 4.5. I'm going to do an additional value. I'm running out of screen space below, but I'm going to write it up here in the top right-hand corner. I know that 4 and 16 is a point on my original y equals x squared, and that's going to map to become 4 and 4. So a couple of things here. It may be easier. Half isn't so bad as a fraction, but sometimes you end up with values for your compression that are not such nice fractions, or they may even be decimals, in which case it may be easier to just not really plot the challenging points, but focus on plotting the points that are nice and easy to find on your grid. So I've got 3 of them here, and I'm going to go with that. So I'm going to plot my new graph in green with at 0, 0, and then I've got my 2 and 2, and then I've got 4 and 4 over here. So there I go. I can see that I've got a graph that's quite a bit wider, and I'm going to mirror this on the other side. Of my y-axis. Now I'm going to redo that because I'm really not happy with it, but it should be more like a bowl as opposed to a V, but hard to do again with my stylus. So this is y is equal to 1/2 x squared, and our red graph up here is y equals x squared. So again, what I could have done instead was I could have said, well, I know when I stretch or compress this by a factor of a half, all of my y coordinates become half as tall as they were. So I could have just as easily gone ahead and said, okay, well, this point right here gets to be half as tall, you know, and so on and so forth. So this point right here gets to be half as tall. But the numbers aren't always easy to work with, so that's just simply one strategy that you can use. So again, so far we've talked about reflections, we've talked about vertical stretches and vertical compressions. So here's an example that you might see in some of your practice work. Let's go through it together. It says, without sketching, sometimes you won't be asked to sketch each parabola. State the direction of opening, coordinates of the vertex, equation of axis of symmetry, domain, range, and minimum or minimum value. So I'm going to write a little bit of that out on the side here and come back in a minute. Okay, so here I've set us up nicely to work through this problem. So what I do is I usually remind myself, okay, well, I know that the standard form so far, what we've learned is y equals ax squared, if I'm talking about stretches, compressions, and reflections. And so if I look at, well, what is the value of a here? The value of a is -2. And so I know that this negative right here tells me that this is a reflection. And I know that this 2 here tells me that there's a vertical stretch, factor of 2. So that allows me to kind of do, and this is how I would do this if you were, especially if you were just starting out, might help you to visualize some of the properties that we're asked to identify. So I would say, okay, well, let me do just a quick little sketch of this, y and x. And so I've got here's my standard y equals x squared. And so how is this other graph going to compare? Well, it's reflected, but it's also stretched vertically, so it's going to be about twice as tall, right? Or half as narrow if you want to, or half as wide if you want to think about it that way. But again, we're just doing a sketch here to visualize. So it's going to be upside down, and it's going to be narrower. So let's go and look at the properties that I have on the right-hand side here. So my new graph is going to be opening down, which, you know, maybe you didn't need to visualize that because you know that that's what that negative means. Okay, my vertex, well, I haven't moved my graph at all. So my vertex is where it was before when I had y equals x squared. It's at 0, 0. So that means that my axis of symmetry is still straight down the middle of my graph, and it has the equation x equals 0. My domain, well, my domain is going to be the same as the domain for y equals x squared, which is that, my graph is going to continue to go wider and wider on both the negative and positive x side. And so I can say that x is such that x belongs to the set of real numbers. My range, however, is a little different because I've reflected it. So because I reflected it, my graph has a maximum value at y equals 0, which means that that is a restriction on my range that I have to include. So although y is such that y belongs to the set of real numbers, it's also restricted in that y has to be a value that is less than or equal to 0. Okay, and as discussed, I have definitely a maximum at y equals 0. So hopefully you did okay with that. I have one practice question that I'd like you to try on your own, and then we'll come back together and take it up. Okay, so take a minute, pause the video, and attempt to complete what's being asked of you for y equals 1/2 x squared. Okay, so here I've written out my solution to this problem. I started by identifying my a value, which in this case tells me that because it's a fraction, that it's a vertical compression. So I just kind of tried to visualize what that would look like compared to y equals x squared. It would be y equals 1/2 x squared would be wider because of course I've squished my graph down. The visualization helps me to see that my graph would open up, that my vertex is not changed. My axis of symmetry is not changed either. My domain is going to, this red graph here is going to go wider and wider into the positive and x direction, positive and negative x direction. And so all of the real numbers are included there. But I can see that my range is limited. There's a restriction on my range in that I can't have y values that are less than 0. So my y values have to be greater than or equal to 0. That gives me a minimum at y equals 0. So hopefully you did okay with that. If you struggled with any part of this or with any of the homework, absolutely reach out. I will be assigning you some practice problems so that you can practice this skill and solidify it. And we'll start with a warm-up tomorrow morning.